All right, so the big things we have to look forward to. Woo. All right, exam 3 is next Monday. In class, we'll have the written exam. Monday afternoon, Tuesday, Wednesday, you can take the written exam, and then Wednesday evening to Friday night, you can do the revisions. We have 2 review sessions set up, just like we've had before. Our first one will be on Thursday, 6 to 8 in Woodso 007. Okay. The second one is a SI super session on Friday, 4:30 to 6:20. We think it will also be in Woodso 007, but we're waiting for confirmation on that. Okay, so I'll let you know on that for sure. Yeah. It is confirmed? Okay, good. So this is not to be determined. This is in Woodso 007 as well. Okay, so make sure to hit those. Yesterday, I think it was, or on Monday, I sent out an announcement telling you which problems on the old exams are relevant for us on the upcoming exam. All right, so those are some good places to practice. Okay. So we are in the middle of learning about nucleophilic acyl substitution reactions of carboxylic acid derivatives. We've learned how to name all of those derivatives. We talked about their relative reactivities, and we started through some reactions of the most reactive of those functional groups. All right, so we looked at reactions of acid chlorides and of anhydrides. And remember, in general, the flow of these reactions is always from the most reactive to less reactive. Okay, we can always go downhill in reactivity. Though today we'll look at a way that we can then kind of recycle back up to the top, and so we could go down again. So that's a way to start from something near the bottom and move up. Okay? So today we will look at acyl substitution reactions of esters. I think we have amides next, and then carboxylic acids. All right, so it's going to be an exciting day, believe me. All right, any questions? All right, let's do a clicker. So we kind of highlighting 3 different reactions, okay, and they're all closely related. And so let's just review what we put up here last time. In general, what we're doing, we're just varying these 2 R groups, either between alkyl or hydrogen. All right, the first possibility has the blue R as an alkyl group. Excuse me, so remember this is then an ester reacting with, if the red R is an H, with water, giving us a carboxylic acid and an alcohol. So this is called a hydrolysis reaction. Okay, remember all of the carboxylic acid derivatives give carboxylic acids as hydrolysis products. If we start with R as an alkyl in the second one, again, this is an ester. If the red R is an alkyl group, then we're reacting it with an alcohol. And what we're getting is a different ester plus a different alcohol. Okay, so we're essentially exchanging this R group. All right, so this is called a transesterification. Okay, so transesterification reaction. We're just changing those two groups. And then the bottom possibility, so blue R is an H, so this is a carboxylic acid. Reacting with an alcohol, giving us an ester and water. So this is exactly the reverse reaction as the top one. Okay, it's just going backwards. And so this is called this is named after somebody there. This is called the Fischer esterification. Okay? All three of these reactions have exactly the same mechanism. All right? The only difference is whether those R groups are alkyl groups or H's. Okay? Everything else is the same. All right, so let's look at how this happens. All right, so the first thing is, and I think I mentioned this last time, I didn't write it on the last slide, is that this reaction only takes place for these three if we are in the presence of an acid catalyst. Okay, we talked about how esters are stable in biological systems, right? We need to do something to catalyze the reactions. So chemically, we can do that by just either making the pH low, or we'll see we can also make it high. Okay, but under more neutral conditions, this reaction does not take place in biological systems. They need to have an enzyme that catalyzes the reaction. Okay, so let's just write out the products here. We know that those two groups are going to just exchange places. Right, so we're going to end up with the blue R group over here and the red R group over here. So they're just going to swap over. All right, so what's the acid going to do in this reaction? Other than catalyze the reaction, how is it going to do that? Right, it's going to protonate the carbonyl oxygen, and what effect does that have? Right, it makes the carbonyl carbon more electrophilic, more delta plus. Okay, so we are going to start out by protonating that oxygen. This is the same thing we did when we formed hemiacetals from aldehydes and ketones, right? Okay, so if we do that, we add our H plus there. Okay, it increases the amount of, the other resonance form where we push the electrons on the oxygen, we have a plus on the carbon. Okay, so this is activated now, and it can react with the alcohol. Oops. Okay, so this comes in, reacts with the carbonyl carbon, the electrons go up onto the oxygen, and we generate a tetrahedral intermediate. Okay, these kind of terms, you're probably just getting tired of them because we've gone over some of them so many times. Okay, remember that the H is still intact on this group that just acted as the nucleophile, right? So we go to another tetrahedral intermediate, or this first tetrahedral intermediate, and then we're going to go to a second one where the molecule is neutral. Okay, we're just going to use the alcohol as the base in this case, because usually we're going to have an excess amount of this alcohol to drive the reaction towards the products. So this one is just going to come in here, remove that proton, and we go to a neutral tetrahedral intermediate. One of the R groups is the red one, the other one is the blue, and the third group up here is the alcohol. Okay? So at this point, if we look up at our reaction and we see what we want to do, we can decide what we have to do on our mechanism. Okay? So we know what we're doing is we want to get rid of the group with the blue R, right? And we want to keep the one with the red R. So we want to protonate on the oxygen that's connected to the one that's going to be the leaving group that drives us, the other one. No, that one. It drives us toward the products, right? So what happens if we protonate on the O with the red? That just goes backwards, right? This is all in equilibrium. What if we protonate on the OH? We get a water molecule. What can we do from there? Okay, so this would be kind of like chemistry that we did with hemiacetals or acetals. We could do that. You know, that would be a good leaving group, but because both of these oxygens have R groups, there's no way to get to a neutral product by doing that. Okay, so we can't get to a stable product. So even if it does that, it's just going to come back. All right? So if we protonate down here with the blue one, then that can act as the leaving group. Okay, let's see if we can curve our way.
Dr. Davis.
Yeah.
So why can't we stop at the acetal there? If we took off the water, wouldn't it form an acetal?
Okay, so, well, so the question is, why can't we just go to an acetal here? So in order to go to an acetal, we'd have to essentially replace this OH with an H. Okay, so this is because we're starting at a reactant that's in a different oxidation state, essentially. We can't just remove this and just block that and have an acetal here. Okay, because we'd have to have an H, and there's no way to get to there. So, you know, that could come off, but we'd end up having to either have a plus here, or we have the electrons on the oxygen, try to stabilize that, but then we have a double bond of the oxygen with a plus on the oxygen here. All right? There are species that have 3 R groups on here. They're called orthoesters. But they're much harder to form. They're not so stable. Okay? So we are going to protonate now, and I'm just going to use H+. If we wanted to, notice what we're forming here, we're picking up the H+ onto this alcohol. So we have actually 2 H's here, and this would be very much like hydronium ion. Okay, it would be kind of shuttling. So the alcohol is acting as a proton shuttle. All right, so we want to get rid of the blue group. So we're going to protonate on that side to make it into a good leaving group. Could somebody maybe close that door back there? Yeah, question.
So, just so I'm clear, we're protonating there just to get the mechanism, but it could protonate either.
It could, yes. Well, so in fact, protonating on the red one just goes right to here.
And then it would reverse, and so you're assuming that it's going to go forward eventually.
Well, yeah, here, let me address that in just a minute. Okay? All right, so we're going to try to protonate here. Let's see if I can fit this all in. H. And here's our blue one on there, and our red one on here, and we have a plus on this oxygen now. All right, so that can come off. Right, so this is a good leaving group, just like water is a good leaving group. Okay? Alcohol is really an equally good leaving group as water is. And that would form a carbocation, but what we usually do is just go directly to the more stable resonance form, and that is where this oxygen donates its electrons down to form a carbon-oxygen double bond. So why is this resonance structure that we're going to, why is it more stable than just the carbocation? Because all of the atoms, all of the oxygens and carbons all have complete octets of electrons. If we draw the plus on the carbon, then we are drawing a structure that only has 6 electrons around the carbon. Okay, so that resonance structure is less stable. Even though we know the plus is actually spread between those two positions. Okay, so now we've gone to here, and we've kind of kicked out that alcohol. All right, and so now we just have to, what do we have to do to get to the product up here? We just have to deprotonate it. Okay, I'm going to put my air on the other side. This way and this way. So I'm just going to use another alcohol. Should have drawn the OH the other way. Okay, so these electrons are just going to come over here and pull off this proton. Okay, and that gets us to our product. Okay, so the question was, when we're in here in the middle, you know, we have all of these oxygens, especially here in the this is like the symmetrical middle of this mechanism, right? How do we know where it protonates? So it can protonate any of these places. All right, if it protonates on the OH, it's not a constructive place to protonate. It can't go to a stable product. So it's always going to come back to here. If it protonates on the red, oxygen next to the red, it just goes back to reactants. If it protonates on the oxygen with the blue, we can go towards our products. Okay, so we are going between, you know, either an ester and an acid, or 2 esters, and these have relatively equal stabilities, all right? So if we just let the reaction go, if we put equal amounts, so if we go 1-to-1 ratio over here, right, then we'll probably get about a 1-to-1 mixture of these, okay? Because the acids, or the 2 esters, they're all about relatively equal energies. Okay? So we get an equal mixture. So this is where we have to play with the equilibrium, right? We have to use the Chapelier's principle and to drive the reaction in one direction or another. Okay, so in general, what we can do is if we use an excess of this alcohol or water, if we're doing a hydrolysis, then it will drive the reaction in this direction. Okay? If we want to go back the other way, which is really just one of the forward reactions that we did, we had these two as reactants. We didn't want to go back that way. We just use an excess of this alcohol or water. Okay, so we always just use an excess of the water or the alcohol, which is the reactant side, and that will drive the reaction towards the products. It will shift the equilibrium towards the products. Okay? Okay. So like I said, you know, whether we go forward or back, this is all the same. So let's just, I guess let's just draw out maybe a specific example down here at the bottom, so this isn't so kind of abstract, right? So we could just say, okay, here, here's an ester, okay? And we want to exchange that methoxy group. Let's say we use something like isopropanol, okay? And we add a small amount of acid. Oftentimes sulfuric acid is a common one for this. If we use an excess of isopropanol, then we can drive this transesterification reaction towards the products. Okay, and what we're going to get is the alkyl group on the ester is going to be exchanged for what was the alcohol plus methanol. Okay? If we started with this ester over here and we wanted to hydrolyze it to give us a carboxylic acid and methanol, what would we react it with? Just water, right? Here, let's add in another slide here. So let's just pick another. I'll put a benzene on here. What if we have this ester, okay? And we do a hydrolysis reaction. So I'm just going to draw it like this. I'm going to say we're going to use H2O and H+. Okay? And so in this reaction, this bond here is going to become cleaved. We're going to get a carboxylic acid. On this side. And the alcohol of the ester on the other side. Okay, so this is a hydrolysis reaction. If we start with something like, I'll make a ring, but I won't make it into benzene this time to really mix it up here. So we start with this acid and we want to form an ester. Okay, let's say we're going to react this with phenol. And we're going to add some acid into this. Okay, mechanism is just the same. If you use the excess of phenol, or maybe this is a good place that I could show you another way to do that. Okay, and then we get this plus water. Okay, this is called the Fischer esterification. Okay, same mechanism. So in this case, we have kind of two molecules here that will have reactants that have kind of higher boiling points. Okay, so we can use another trick to drive this reaction towards products, and that involves removing the water. Okay, so that has the same effect. We pull away one of the reactants, it also drives the reaction to the product. And here, let me use my artistic skills again to show you kind of a cool apparatus that you can use in the lab to do this. This is kind of ingenious. Okay, so here's our reaction flask. Okay? Into this, we put a glass piece that looks like this, and then it has like a side arm that comes down like this. Sometimes that, if you're doing it kind of on a larger scale, that side arm might have a little valve, a little stopcock on the bottom. And then on the top up here, we put a water condenser. Okay? So, in our flask, we put our two reactants, and we are going to run this reaction. Most commonly, for the solvent, we're going to use benzene. Okay, this is our solvent. And we're going to use benzene for two reasons. One, it's less dense than water. And two, because benzene forms what we call an azeotrope with water. Anybody know what an azeotrope is? In the old days, you'd learn all this stuff in lab. You kind of skim over these things now. Okay, so an azeotrope. Okay, this is where we have a mixture of two solvents, and the boiling point of the mixture is lower than the boiling point of either of the two pure solvents. Okay? So there's a ratio of benzene to water, mostly benzene and a small amount of water, that has a lower boiling point than either benzene or water. Okay? Azeotrope is where we have a mixture has lower boiling point than the pure solvents. Okay, so what we also do is we fill up here, we put some benzene up in here. Oops, benzene. Okay, so then what we do is we reflux this. Oops. You guys know what reflux is, right? Boiling. Right? It's a fancy organic chemist's way to say boiling. So we reflux this, okay? And at the beginning, it's just benzene that's refluxing. And the vapors go up this tube, they go all the way up here into the condenser, and they drip down into this side arm. Right? And this thing just overflows, and the solvent just runs back into the flask. All right? But as the reaction proceeds, the first thing that's the vapors coming up here is going to be azeotrope. So this is going to be the mixture. So benzene is going to carry water up here. It's going to go up into the condenser. It's going to condense. But then it drips in here, and the azeotrope separates, and the water is more dense than benzene, and the water sinks to the bottom of this side arm. Cool, huh? And the benzene floats on top, and it just runs back into your flask. Okay, so you're never getting rid of the solvent, but the azeotrope, so this is going up here, and then it comes back down in here, and then the water collects at the bottom. Okay, so you just keep running the reaction. You keep removing water as the reaction proceeds, drives this reaction all the way to products. Okay, even though the reactants and the products are roughly the same energy. Okay? So there are so that is kind of ingenious, don't you think? Your life just wouldn't have been the same if you didn't learn about this right now. All right, well, so let's get back to it. All right, so these, like I said, the bottom line is here. All these are the same reaction, okay? They have some different names, but they're all doing exactly the same thing. The mechanism is exactly the same, okay? And the mechanism is really kind of related to that, acetal formation or acetal hydrolysis. It all involves acid catalysis, so all the reactants in these mechanisms have two possibilities. They can either be neutral or what? Or protonated as cations. Okay? They have to be either neutral or acidic. Neutral or cations. All right? And the acid-catalyzed reactions, we're never, ever, ever going to have an anion. Okay? So if you have the urge to draw an anion on maybe an exam next week and it's an acid-catalyzed reaction, don't do it. Okay? I'm just giving you a hint. All right. So that doesn't mean that we can't do this same reaction under basic conditions. All right? And so in essence, because esters are less reactive, we either have to use a catalyst or a stronger nucleophile. Right? And a strong nucleophile here is hydroxide. Okay? So we can do this. And so let's draw out. I drew an example of this on Monday. So if we just draw out what the initial products would be, we'd get this carboxylic acid plus ethoxide. Okay, and what did I say happens from here? What general kind of reaction is going to take place? Acid-base reaction. Okay, because ethoxide is a strong base. So this is going to pull off this proton. And it's going to go to the carboxylate anion plus the alcohol. All right. So that's the end of the reaction. So let's look at how it takes place at the beginning. So what's going to be the first step of this mechanism? Are we going to protonate? No, we don't have any protons. We don't have any acidic protons around. This is in basic conditions. There's no acidic protons. We have a better nucleophile, so it can now directly attack the carbonyl. Okay, just like the other strong nucleophiles we saw, like Grignard reagents, or acetylide anions, organolithiums, all of these can directly attack the carbonyl because they're very strong nucleophiles. Okay, so we go to a tetrahedral intermediate, OH, like this. And because we're in basic conditions, and hydroxide is in there, then ethoxide is just as good of a leaving group as hydroxide is. All right, so we can show this reaction. So these electrons can just come down directly and kick out ethoxide. And this goes straight to these products right here. Okay, so we have the OH still on there. That goes straight to the carboxylic acid. Kick out ethoxide. And then once those are formed, we do an acid-base reaction that gets to these final products. Okay? So in this case, if we just look at the reactants over here and the initial products, these are essentially almost equal in energy. Like we saw before, we would get essentially a one-to-one mixture of those. But because this reacts with acid-base chemistry to react further, now we have this carboxylate anion, and where is the carboxylate anion in the list of relative reactivities of all of those carboxylic acid derivatives. It's clear on the bottom. Okay, so now what we've in essence done is gone from kind of a carboxylic acid derivative with a moderate reactivity to one that's very unreactive. Okay, so we're going downhill in energy. And so this one will automatically go completely to products. Okay, this reaction has kind of a common name. This is oftentimes called a saponification. All right, and this has a practical application as well, this reaction. Okay, so here's the practical application. So I'm going to draw this like this. This is going to be, okay, I'm not going to count the lengths of these chains. Who knows what this is? Huh? Yeah, this is a triglyceride. Okay, this is a common fat. Okay, there's various carbon chains here. In the body, they may have double bonds in them. In animals, usually the double bonds are cis rather than trans. Okay, and so this is a common fat. All right, so if we react this with, say, something like potassium hydroxide, okay, which has, sometimes it's in gram, you can even dig it out. What's it called in a common sense? If you were like a pioneer, the KOH. This is called lye. Okay? And what happens is it does a saponification reaction. All right? And so what we're going to get, is this is a 3-carbon, a triol. This is glycerol. And we get 3 of this, whatever these carboxylate anions are. Okay? And this is essentially what soap is. Okay, so the way soap, do you guys know how soap works? How to get like greasy stuff out? Yeah, it forms what they call a micelle. Okay, and the micelle, so let's just draw each of these little soaps. I'm going to draw it like this with a minus charge because it has this hydrophilic end, loves water. And it has this long chain, and this is a hydrophobic end, right? And if you put this in water, then the hydrophobic ends try to hide. They're scared of the water, right? And they try to hide from the water. The hydrophilic ends love the water, and so they want to hang out with the water. And so what happens, though I kind of drew this the wrong way, all of these polar ends are going to orient to the outside, and all of the hydrophobic ends are going to orient to the inside. Okay, so this forms what's called a micelle. Okay, so if you have something greasy, then this is like greasy in the middle. Okay, it's all these long chain alkyl groups. And so the greasy part can dissolve in here, and then the micelle just carries it away. Right? It's not really dissolved, it's in like little teeny like bubbles or something like that, these little micelles. Okay? All right, so, yeah.
So
What is the definition of saponification? I know we just did it in the lab with the
Oh, okay.
salicylic, like making the salicylic acid, I think.
Okay, yeah. You started with methyl salicylate or something like that, spearmint oil or something like that.
Yeah, so I'm just curious what the definition is.
The definition, saponification is just a common name for base-promoted ester hydrolysis. Okay, it's just what they call it. I call it saponification, I call it soapification.
Yeah.
Okay, yeah, so there's the reaction. Perfect timing. All right, so now what do we got to do? So those are the reactions of esters. Okay, esters, you can actually go from esters to amides as well, because it's going downhill in energy. Okay, but let's look at the reactions of carboxylic acids, or of amides. We'll get back to carboxylic acids. All right, so we can hydrolyze amides as well, but we have to kind of beat on them even harder, because amides are less reactive. And this is, in essence, going a little bit uphill in energy, so we have to probably heat this and use an excess of water. Okay, so if this is an acid, we can go to the carboxylic acid plus water. So you can actually take, and this is one way if you have proteins or small proteins, small peptides, you can, and remember those are made up of amino acids. All the amino acids are linked together by amide bonds. Okay, so you can heat proteins with water and maybe hydrochloric acid or something, and it will cleave all of the amide bonds. You get a whole bunch of just separate amino acids. And then you can analyze those. You can do kind of an amino acid analysis and count how many of those amino acids are available for each one. Yeah, just a second. Yeah.
What happens to the nitrogen?
Oh, good question. Well, we don't really get water out of this, do we? We're adding water in. And so we are going to get, if we're in acidic conditions, we would get the ammonium ion. Is that the same question? Okay. Yeah. Okay, I was just... who knows what I was doing. I was thinking about amino acids and stuff like that. Okay, so this follows just the same mechanism as the ester hydrolysis. Okay? We protonate on the oxygen, water comes in, we end up having to then we have to protonate again on the nitrogen so it can be a good leaving group. We do exactly the same reaction. Okay? Down here is the base promoted hydrolysis, same thing. We get the carboxylate anion plus ammonia. Okay, so under acidic conditions, we have the acidic forms of both the carboxylic acid and the amine. Right, we talked about those back a while ago. And under basic conditions, we get the basic form of both of those products. Okay? The mechanism for the acid-catalyzed hydrolysis would follow that of the ester hydrolysis. The base-promoted amide hydrolysis would follow that for the base-promoted ester hydrolysis. Same mechanisms. Okay? With this slide, so Fischer esterification, so take about 10 seconds and write the product of that Fischer esterification reaction. All right, so all we have to do is draw out this carboxylic acid. We're going to take off the OH of the carboxylic acid. We're going to add the O of that alcohol. And we get a product like this, plus water. All right, we've already done this reaction, right? We went through the whole mechanism and everything. So if we want to start with an acid and we want to make an amide, though, what's going to happen if we mix this carboxylic acid with this primary amine? It's just going to do acid-base chemistry, right? We have an acid, we have a base. Excuse me. We're going to get our conjugate base plus conjugate acid. All right? Turns out that if you heat this a lot, so what they say is like greater than 100 degrees Celsius, you can drive this reaction to an amide. Plus water, I guess. But that's not really a very good reaction. Okay, it's hard to do it. You've got to heat it a lot. Your reactants may not be stable to that. And so we need to take some other strategies here, and our strategies are going to be just like we took when you had an alcohol. What did we do if we wanted to make an alcohol and do a substitution on an alcohol? Well, not protect it. We want this to react. We have essentially we have a bad leaving group now. So we want to make the OH, our strategy is to make this into a better leaving group. Okay, so tomorrow we're going to see a couple of ways to accomplish this. Okay, so I will see you guys tomorrow.